All right. Okay, thank you. Yeah, so my name is Lorenzo Ennoggi, and I'm a PhD student at the Rochester Institute of Technology. And yeah, today I will be telling you a little bit about CarpetX, which is a new driver for the Einstein Toolkit. So this talk was supposed to be given by Erik. Of course, I'm not Erik, so I'm not an expert of all the technicalities and details of CarpetX, but I'll try to do my best, and let's see. So, as I said, CarpetX is a new driver for the toolkit. So, in general, a driver in Cactus, it's something that handles all the computer science, let's say, tasks in a simulation. So, for example, it manages allocation of memory for grid functions, and it takes care of running scheduled functions at the correct time. It takes care of distributing grid functions across multiple processes, multiple nodes, and synchronizing the ghost zones when you have multiple components, multiple refinement levels in your grid. It takes care of actually implementing adaptive mesh refinement. So as we will see, adaptive mesh refinement in this new driver is provided by the AMRX infrastructure. So I will be telling you a little bit about that. There is being recently a focus also on multi-block systems. I think Lucas Sanchez is working with Erik on this, on implementing multi-block system within CarpetX at the moment. And finally, the driver also manages parallel input-output. So we have new formats, new output formats in CarpetX, and I will be telling you a little bit about those as well. So yeah, as I said, CarpetX is based on the AMRX framework, which is an infrastructure, a code infrastructure for adaptive mesh refinement. So this is really adaptive in the sense that Carpet was a fixed, if you want, a fixed mesh refinement infrastructure, in the sense that you decided where to put your grid. AMRX is really adaptive in the sense that you have the criterion whether or not you want to refine your grid or not is local and is decided during the evolution. And I'll tell you a little bit more about this. AMRX is publicly available, is available at it is on GitHub at this address, and it has many users. There are several codes as of now which are built upon AMRX. They all work beautifully. It is a project which is funded by the DOE Exascale Computing Project and has a friendly and competent developer team, so that's nice. And most of all, it is scalable. So that's what the X in AMRX is about. Let's see, we have new capabilities in CarpetX compared to Carpet. So first, CarpetX now, thanks to AMRX actually, it supports cell-centered as well as space or edge or vertex-centered grid functions. So for example, if you want to do GRMHD, you typically want to have the metric terms at the vertices, and for example, the resonance density, pressure, in general hydro variables, you want to have them at the center of your cell. For example, you may want to have magnetic fields, and magnetic fields usually live at the faces. And for example, if you evolve Maxwell's equations with a vector potential formulation, you may have the vector potential living on the edges of your numerical cell. So these are all potentially needed, and this is important in order to ensure conservation of, for example, the resonance density. When you do hydro, or conservation of the constraints, such as the solenoidal constraint. CarpetX also, again, thanks to AMRX, also implements refluxing. So this means that if you have a coarse grid and a finer grid, you compute the fluxes of some quantity on the coarse grid, then you move to the finer grid, and then you feed back let's say the coarse grid with the fluxes you computed with from the finest grid, and this ensures much better conservation. For example, let's say the magnetic flux, for example, at refinement boundaries. So this is very important. As I mentioned before, CarpetX supports adaptive mesh refinement, which is really adaptive in the sense that it's based on local criteria. This means that you have, imagine you have your cell, you associate some kind of error to your numerical cell, and you decide on a threshold, which is user defined, and if in that cell this error goes above your threshold, then you refine. Okay, so it's really local and it's really adaptive. There is efficient multi-threading through OpenMP, which, from what I know, is a little bit different from the multi-threading which we are used to from Carpet. Because in Carpet we had, for example, imagine 2 components on the grid. Each component is assigned to a different thread, and but looping over each of the components is doing serially. While in AMRX, the logic is a little bit different. You divide your components in tiles, which have a definite tile size, which you can define, user can define. And then basically at the end of the day, you have much more parallelism and so much more efficiency. So this is, again, thanks to AMRX. This here is very important. There is CUDA support. Again, this comes from AMRX. This is very important, especially as of today, right? Because there's many investment in GPU cluster, for example. So having CUDA support is really looking towards the future. And we will talk about how to write code which is CUDA compatible during the tutorial, which will be in the final part of the day. CarpetX also has an elliptic solver implemented. And as I said before, there is efficient parallel input-output. So we have new data formats, for example, ADOS2 or Silo, which is the native format for visit. Or we also have OpenPMD, which is really cool. You have in OpenPMD, essentially you have a series, what is called a series, which contains all your iterations, and each iteration contains records, okay, which could be, you can imagine a record, it could be the resonance density, for example, or the magnetic field. and each record can have one or more components. So, for example, the resonance density is a scalar, right? So it will only have one component, but the magnetic field or the velocity will have three components, and so on. So this is cool. So yeah, adaptive mesh refinement within AMRX, essentially. This image here comes from the AMRX documentation, and grid function can live either at vertices, as I said before, for example, the metric. They can live at cell centers or faces of edges, as I mentioned before. And for adaptive mesh refinement to work, what AMRX does is flag in the cells that should be refined. And if you have, multiple neighboring cells which should be refined, then those AMRX takes care of enclosing those regions in rectangular blocks, which will then be refined. Okay, again about CUDA. So actually, in CarpetX, you don't need to bother about CUDA, essentially. So you don't need to bother about CUDA keywords, all those boilerplate CUDA code, CUDA infrastructure. In CarpetX, you can easily write code that runs on both CPUs and GPUs. So really, the same piece of code can be compiled to run either on CPUs or on GPUs. It looks like regular CPU code. And for example, when you write a loop, you will see this again during the tutorial later. But when you write a loop, if you're running on a CPU, then it will be a multi-threaded CPU loop. While if you are on a GPU, it will actually run on the GPU. Okay, but the code, the actual code you see and you write looks the same, so you don't have to worry about CUDA. As I mentioned before, yeah, we have an elliptic solver implemented. There is a new thorn, which is called PD solvers, which interfaces to PATC and can solve arbitrary elliptic equations. It supports many different solvers and preconditioners, again, using PATC. And it uses automatic differentiation, which is cool, to calculate the Jacobian from the residual. And yeah, as I mentioned before, we have efficient parallel input-output. So the problem is that parallel file systems exist, but they can be quite slow if you don't use them correctly. So as I mentioned before, you can use in CarpetX, you can use OpenPMD, which is actually based on ADS2. And they're both very efficient. And we'll see again, we'll see an example of, running a simulation with CarpetX and visualizing OpenPMD output during the tutorial later. But we are looking actually for volunteers to add OpenPMD support to various post-processing and visualization tools. I would think about, for example, Qubit or PostCactus, for example. And yeah, as a fallback, as I said before, CarpetX also supports Silo, which is the native format from Visit. However, this is a bit slower than the other two, so it's not. If you can use the other two, that's better. That's better. Okay, here I'm going to show a weak scaling test done with CarpetX, done on Summit on GPUs, evolving the Z4C system in Unigrid. So here we show 3 different problem sizes, and you see that basically the scalability is perfect from 1 to 1,000 nodes. So I mean the curve is flat as you would expect. So that's really good. However, the efficiency is not that good because we were expecting more than 10% efficiency, while we get around 0 point something, depending on the problem size, 0.4. Sorry. The cause of this is known. Is because the compiler does not optimize very well, and so another thing which is currently missing in CarpetX, but potentially can ameliorate this problem, is maybe automatic code generation. And I'm thinking about NERPy, for example. Okay, here, yeah, I don't have the actual movie for this QC0 black hole binary simulation. But yeah, it was just to show that, you know, the QC0 run works beautifully. So this is very good. So just to give a brief summary and conclude, CarpetX is ready to be used for prototyping and testing. It is available, it's publicly available here from Bitbucket on AMReX repository. And I encourage you to join our GitHub channel here. And stay tuned. Let me also add, stay tuned for the new GRMHD, well, GRHD for now, because we don't have magnetic fields. So GRHD code, which is called AMRX, and which we will speak about that during the tutorial later. So this is work in progress, but up to now it's working beautifully. So stay tuned for that. So I'm a bit ahead of time. So let's see what I can tell you.
Okay, Lorenzo, thank you for giving the presentation. I have a cough, so I often cough when I talk, so but couldn't give that presentation. Thank you for jumping in. And people pointed in the chat to YouTube rendering of the video that you couldn't show. I don't know whether you can go to YouTube and show the video.
Sure. There we go. Let me just play it from the beginning. There was no apparent horizon finder here, right?
No, that movie is a bit old, probably more than a year old, and it was just the time evolution.
Yeah. But yeah.
So yeah, this. Shopify, il servizio che uso da anni ormai per vendere i miei lavori online.
This was.
Yeah, were you able to get to merger?
I'm sorry, can you repeat the question?
Yes.
I muted my audio because there was an advertisement on YouTube. Sorry.
Yes, that goes up to merger and beyond, but there's no gravitational wave extraction and there's no horizons. Actually, the movie is more than 2 years old, as I just see from the timestamp.
Okay. Oh, we have a couple of hands raised, if that's okay. So Roland?
We do actually have, not for this particular one, but we do have gravitational wave extraction for QC0.
Ooh.
Let me paste the link somewhere here. That was done with that same code, but with a little bit of an extra hack thing. So there's multiple people working on this, and multiple prompts where we get things. So we do have gravitational waves that in principle come out of that. They do look exactly like QC0 waves should look like. Put that into
Great. Yeah, so Roland will share with everyone a gravitational wave extracted from QC0 in a parallel line of development. So appropriate, right? Parallel. Good. So let's see. Would it be okay, Erik and Lorenzo, if we took a few questions, because we have some hands raised in the in-person audience?
Yeah.
Would that be okay?
Okay for me. Yeah.
Okay, great. Yeah, go ahead.
I'm just curious. So is it going to be so CarpetX going to be inherently only AMR, or you also going to offer like a box in a box, maybe just an emulation of something more significant where you have also the staggered ghost zones at close line boundaries, or you only going to do AMR?
Yeah. So I think the question was, are you only going to do AMR, or are you going to also have a capability of doing box in box?
You can do box in box. That is rather easy to set up. There's a thorn for that.
Cool. All right. Steve has a question. Sorry.
Yeah, I'm sorry. There was a slide where it said something about automatic differentiation. How does that come about?
Okay, Steve. Yeah, I forgot to actually prepare one slide, because one of the major features about CarpetX is a feature on which Steve worked a lot, and he has been pushing that for years. And that is make the simulations much safer. It is all the scheduled functions now declare which grid functions they read and which they write and which are synchronized and so on. And if there's an inconsistency, the driver checks that and flags that. That is, if there's any kind of scheduling problem, it is now much more likely to be detected. And I was very annoyed at myself that I consider myself fluent in Cactus. It's basically impossible for me to write a perfect schedule. And I have come to the idea that there's probably bugs in lots of codes that I wrote that I never noticed. So this feature is really important. That's going to eliminate lots of bugs where ghost zones are incorrectly set, or boundary conditions missing, or some grid poll values used from previous iterations. So Steve, thank you for pushing that. I'm sorry that I didn't add the slide into the presentation for that.
That's fine. But automatic differentiation, I thought that would be, I was just wondering, I thought that was some calculus thing.
Okay, yes. So automatic differentiation has seen a resurgence since machine learning popped up, because you have these big neural networks and you want to kind of optimize them. You need to calculate the gradient, and manual it's impossible. So there are lots of tools for automatic differentiation. And one of them is based on what is called dual numbers. They're a bit like complex numbers. They consist of two parts, a real part and a part that is the derivative of that value with respect to some quantity. And you kind of calculate both. And from the outside, it looks like a real number. And there's a dual number class that we implemented in CarpetX. And if you use this class instead of regular double precision, when you evaluate the residual, then you get the residual and also the derivative of the residual with respect to the input values, which is the Jacobian.
I'd be interested
So
in learning.
it happens on the level of C++ and essentially the new classes and operator overloading.
Thank you. So we have an online person with her hand raised, Manuela.
Hello, guys. Do you hear me?
We can hear you great.
Okay, because I'm on a cell phone. So my question, by the way, great talk, Lorenzo. I think my question is related to the fact that we would like eventually to use CarpetX also for codes that use curvilinear coordinates, things like circular or other coordinates. There's giraffe. There are other type of codes that will be benefiting from CarpetX. And the question is, and I asked you this a while ago, but I don't know if you remember, Erik. It's whether there is a capability in AMRX to refine and de-refine in some directions. So, like for example, you want to refine in R, you want to de-refine in theta. in spherical coordinates. So I was wondering if AMRX has that kind of flexibility, and yeah, so if you can comment on that.
Good question. So in principle, it does. Whenever you specify refinement in each direction independently. So you pass 2, 2, 2 if you want to refine by a factor of 2. But on the other hand, certain things internally need to be implemented to support a certain kind of prolongation restriction operators. And I don't know what is implemented in that respect and what not. I think if it's missing, it would be straightforward to add, but I'm not sure whether it works out of the box.
Okay, thank you. Okay, straightforward. Okay, I'll take your word.
Great. All right, Gabriel, sorry.
Yes. So you had a lot of scaling, but it was not clear to me what was shown. Like, is this weak scaling? Is it strong scaling? What is the efficiency? 0.1% seems extremely small. Can you explain it?
So this is weak scaling. As we go to more nodes, we also increase the problem size. We keep the problem size fixed at, I believe, 500 cubed grid points per node or per GPU? Per GPU, I think. And there are 6 GPUs per node. So this goes up to 6,000 GPUs. So weak scaling, and we expect a flat line, and that is pretty good. The efficiency is that you calculate the number of floating point operations that the code needs to do, and you divide that by the number of floating point operations that the hardware can do in the same time. And a good code should be somewhere between 1 and 10%, maybe 5 for a good code, 15 for an amazing code, and we are below 1%. And that means the code is inefficient. And we looked at the code and we know why that is the reason. The code is written in C++ with lots of complex structs and so on that need to be simplified, and the compilers don't do it. And the solution is to not use C++, but use something else, such as Python, that runs ahead of time and that produces a simple and straightforward code, and to kind of spoon feed that to a compiler, and then it's much simpler code, and the compiler can actually produce much better code. So if we look at the machine code here, the compiler does do absolutely bonkers stuff. So it just takes some variable, it writes it on the stack, and then it reads it back from the stack with different registers and writes it into different places on the stack, and then it reads it back from there, and then it never uses the values. So very clearly, the optimizer has gone into la-la land. And we talked with the compiler developers, and they said, yeah, it's a complicated problem. The code is too complicated. And maybe you can set these parameters. And we tried. And I think compilers are a black box. You want to use in part of your code optimization pipeline, something where you have much more control. And that's automated code generation. So with McLachlan, we went to more than 10% here. Well, on CPUs, I don't know what GPUs would be. So I think there's kind of an order of magnitude that we could gain from NeRPi. And I think it is, again, Steve who was looking into NeRPi for CarpetX. So
yes,
maybe Steve has some update?
Yes.
10 minutes.
I can just make a comment on McLachlan that UA compilers cannot compile McLachlan exactly because it's super involved. So they fail in optimizing the code. So I don't know if eventually we're going to run into the same issue, which the computer generated code cannot be optimized by the compiler. It's too complex.
Really? I was not aware of that. So both GCC and Clang can digest the code that was generated by Crank. And I'm sure for NeRPi as well. But I mean, we can go lower level. We can produce assembler code in code generations. So I mean, I'm just tired of all these things. I mean, it's just
I'm with you. 100%. Yeah, we had just a couple more questions.
Yeah, you mentioned that you Clang. Were you using Clang with CarpetX? Because I mean, in principle, Clang is doing kind of a remapping of the C++ code to a common language before compiling. And does that not get around any of these sort of inefficiencies?
I'm sorry, I didn't quite hear you. There was a bit of an echo.
So the
Can
question
you get
is,
close?
so the question is, Clang takes C++, converts it into a common language, and then compiles that common language. Wouldn't that get around some of these issues with trying to over-optimize C++ code?
I think it would. That's what I meant. I didn't actually mean assembler, but I meant one of these intermediate languages, LLVM, or maybe even WebASM or something crazy like that. But these languages are still kind of human readable, and you can produce them and they're target independent. I don't want to go there, but we could.
We have one more question, I think.
Also, Mr. Martin, I have a question. So I was, whenever a GPU is applied somewhere, you see orders of magnitude improvements. Like, do you see that already for numerical relativity? Since I always had the expression numerical relativity wasn't the right thing to put on a GPU. Maybe that's somewhat my bias here. Or do we have to wait maybe another generation of GPUs with larger VRAM that it's really gonna explode for us? Maybe.
So I think 10 years ago, GPUs were not ready, but now they are ready because the amount of memory per GPU is good enough that we get. And also, I mean, for many years now, you can buy GPUs that support double precision operations efficiently. That's the case. Now, in these orders of magnitude improvements, when you go from CPU to GPU, they're very easy to achieve. You just need to compare apples to oranges. And people just take an old CPU code that is not optimized, written by the professor 20 years ago, and then a student rewrites the code from scratch, leaves out half of the features that are difficult to implement, and looks at the performance, and lo and behold, the thing is good. But if you take the same GPU code and run it back on a CPU, it also runs much better than the original code. So you can look at the hardware and compare performance numbers, what the hardware promises in terms of flops, and you compare things with roughly equivalent price or something. And there's about a factor of 5 that GPUs are faster than CPUs. And they're also more difficult to program. So if you're lucky, you get a factor of several improvement, probably not 5. But if you get a factor of 20, then that just means your CPU code was bad because the hardware doesn't give that.
Thank you. All right. So, sorry we interrupted. I think Lorenzo, you're going to show us something else.
Maybe I can show. Let's see. Maybe there were some things that came to my mind. For example, how you actually, so the interface, for example, is a little bit different in CarpetX compared to the Carpet interface. Maybe Erik, you can correct me here if I'm wrong, but so my understanding is now that with CarpetX, so just to give you a reference, this is the interface of AMRX, which is the new GRHD Thor, which is under development now. You can add, so first of all, you add this centering keyword here.
5 minutes.
To tell Cactus that this is going to be, for example, this is the conserved momentum, right? So this is going to be self-centered, right? CCC. And you can also add tags to tell the equivalent of the method of line store, which is now called something like ODE solvers. Let me see. Anyway, you can just add this tag to tell the equivalent of the method of line thorn what's the right-hand side which is to be associated to this group. So in this case, the right-hand side is mom RHS, which is here. Okay, so you don't have to manually register the right-hand side. Is that right, Erik?
That is correct. Thank you.
Okay. Yeah. Yeah, that's a feature I wanted to highlight. Let's see. yeah. Importantly, as Erik mentioned before, you need now to add reads and writes statements in the schedule. So this was already, you could do it in Carpet, but it was not compulsory. Now it is. It is compulsory. So, and also let me say that because of this, you need to add a parameter to any of your parameter files which uses CarpetX, which is called cactus presync. Let me open maybe a sample parameter file. Let's see. Oh, presync. Yeah, this one. Cactus presync mode must be equal to mixed minus error. So that enables the cross check of the scheduling between the Cactus Flash and the driver. So you need to have this parameter set. If I'm not wrong, Erik, right? So
it's all correct. Thank you for pointing that out.
Yeah. Let's see if there is any other. Yeah, as I said, ODE solvers replaces MOL, metal of lines. And let's see. Oh, maybe this one, prolongation type, DDF. So again, my understanding is this means that you
2 minutes.
Cell-centered variable grid functions must be, when you prolongate them, this is somehow a cell averaged prolongation, while if you are prolongating vertex-centered grid function, for example, the metric, this is a simple interpolation. So this is, I guess, the advised type of prolongation you want to use in CarpetX. Yeah, I think that's about it. Again, you could, output, as I said, there is silo format, or you could do something like open PMD, all right? I think ADS2 also works like this.
1 minute, please conclude.
Yeah, I think that's about it. Let's see. And I'm not sure, maybe as a last thing, maybe Erik, you can comment quickly on this. What is the actual criterion to refine now, as of now?
There's this grid function regrid error that is supposed to be set by a mechanism where you define how big the actual local error is. And if that variable is larger than a certain threshold, then the respective grid cells and the ones around it will be refined.
Okay. Yeah, I guess that's about it.
Excellent. Well, thank you, Lorenzo. Let's give him a. And thank you, Erik, as well. I know you prepared that presentation and answered many questions so far. We have another question from the audience.
Yeah, since you mentioned that CarpetX is ready for prototyping, does that mean that a lot of the syntax and structural requirements are kind of set in stone, or for example, your scheduling, right? It's now mandatory. Like, are a lot of those syntax requirements set in stone by now, or do you still consider?
Can you repeat kindly the question?
So it had to do with syntax that may or may not be set in stone. Are you referring to like the
Our changes between Carpet and CarpetX requirements and parameter files, like files.
Yeah, parameter files too. Yeah. There are certain incompatibilities that from the original Carpet to the new Carpet. Are all these incompatibilities now stable? Have they been solidified? Is it are we now ready? I guess, and follow-up question would be, are we now ready to start building our codes, migrating over to this without fear that the carpet will be moved out from under us?
Yes, good question. So we tried long and hard to keep things compatible, but unfortunately, certain things just have changed, and some of them are due to decisions made in AMReX. And we tried to keep things compatible, and Roland Haas has pushed a lot for it. But it turns out, also due to the differences in how things are parallelized via OpenMP and so on, it's just not possible. And therefore, I think things will need to be slightly updated to work with CarpetX. And we've begun to write production thorns with it, and we have no plans to change the syntax for anything. And so I think you're ready to port your thorns, but if you do that, please stay in contact with us or attend the AMReX tutorial this afternoon where things will be explained, how to do things. And we're still working on removing some boilerplate and making certain things simpler. But that doesn't change things in an incompatible way.
Great, thanks. And just as a friendly reminder, we have two very related talks this afternoon. Steve's going to give us a tutorial on automatically generating carpet and CarpetX thorns with NERPy, and Lorenzo Ennoggi, Jay Kalanani, and Fede Lopez Armengol are going to be telling us a little bit about GPUs and the Einstein Toolkit, which is very closely related to the work that you just saw. So, so just wanted to advertise that. So please stay tuned. Those will be the last two sessions of the day. There will be tutorials. So we're very excited to see them. All right. Anything else before we wrap up?
As a reminder, during that tutorial, you will, as Erik mentioned, you will actually see a piece of code from AMReX, and so you will see how the actual new syntax works in order to access grid function and how to loop over GPUs. All that is covered in the tutorial. So yeah, stay tuned.
Great. Well, let's thank Lorenzo and Erik again.